Section 1.3 Thinking like a Scientist. Here's our objectives. First, describe how Lavoisier transformed chemistry. Second, identify 3 steps in the scientific method. And third, explain why collaboration and communication are important in science. All right. The first thing, if you go back far enough, you first really kind of start thinking about science, scientists and chemists and things. Really the first idea comes with alchemists. And what they were trying to do, now is a little different than what we do today, but they were trying to find a way to turn things into gold. But this is really the first time that we've started to come up with tools, with techniques for different things, for working with chemicals. And a lot of the, just a simple flask, mortar, pestle, things like that, a lot of those things that we use even nowadays was created back in the alchemist time. And it wasn't always the best way. They didn't always follow great scientific procedures and methods, but it did get us started. And then along comes a guy named Lavoisier, and he really was kind of the guy who did a lot to change science and really came up with the idea of using the scientific method, of making lots of observations and things like that. And this had been he would be in the late 1700s. He's in France and so on. And one of the first things that he did was kind of prove, they had this idea or this theory back then that things that burned contain this substance which they called phlogiston. And when you burn something, like you burned a piece of paper, you burned a wood, some wood, a log or something like that, the phlogiston would be removed from it. It would dissipate into the air as you did it. And if things didn't burn, they didn't contain this phlogiston. Well, Lavoisier kind of proved that, it really wasn't phlogiston. There wasn't such a thing. But what you did need was oxygen. And so he proved that you couldn't burn something without oxygen, and also, things that could burn. See, one of the problems with this idea of phlogiston was, like, if you burn certain things, like metals, like if you take magnesium and burn it, it actually gets heavier. And so there's a problem. See, the original idea is, oh, well, I burn a piece of paper, there's not as much left, something is left, that's the phlogiston, it's gone, I can't get it back. But, that didn't work for everything. And so, Lavoisier comes along, makes some really good, accurate measurements, kind of created a balance that could measure things. I think, what did they say, to the nearest 0.0005 grams. That's pretty amazing for that time period. Created balances like that and measured this stuff very, very precisely. And then eventually proved that it takes oxygen in order to burn anything. And the oxygen was the important part. So this kind of begins the idea of the scientific method. And the scientific method is simply a logical system of problem solving. And you know what? You use the scientific method all the time. You don't call it that, but you use it, every day. So for instance, let's just say that you get out a flashlight and you turn it on and it doesn't work. If you think about it, the most likely thing you're going to say is, the batteries are dead. So then what are you going to do? Well, you're probably going to go and you're going to change the batteries out, turn it on, see if it works. And if it works, hey, you were right. And if it doesn't work, then maybe it's not the batteries, maybe it's the light bulb. And so then you maybe go change the light bulb. And now if it works, hey, it's good. And if it still doesn't work, maybe come up with another idea, or maybe you just go throw the flashlight away and go get a different one. But that's the scientific method, and you do those kind of things all the time. They start off with making observations, like, hey, I turned the flashlight on, it didn't work. That's an observation. And then you came up with a hypothesis. You know what, I think it's because the batteries are dead. And you go test it. The way you tested it, put in a new pair of batteries, see if it works. And then from that, you might have come up with your conclusion, We probably aren't going to go create a lot of theories out of my flashlight idea, but we came up with a conclusion that yeah, it was the batteries because now the flashlight works, or it was something else, and I had to go on. But in the science, from that point on, they might start to develop theories and various things beyond that. Okay, so let's take a look. Hypothesis. What are we talking about? Well, I think most of you know. You guys would all say, hypothesis. I know what that is. Yeah, it's an educated guess, right? That's usually what we're talking about. That's kind of the idea of what you were taught back in elementary school. So a hypothesis, educated guess, or a proposed explanation for what we see happening. We think that it's this. My car doesn't start because XYZ. I'm out of gas, my battery's dead, whatever. Left it, didn't leave it, and put it in park. And then from that we experiment. So we might experiment by changing the batteries. Maybe I go put some gas in my car, go change the battery in the car, whatever. That's my experiment. An experiment is a process or a procedure where we're going to test that hypothesis. And when you do an experiment, you should make sure that you only change one thing. For instance, if I were to go change the batteries and the light bulb and turn it on and then it works, I don't know which one of those two fixed the problem. So while, for my idea of the flashlight, that's probably okay because I don't really care that much. But in science, I do care. I want to know which one it is. So I really don't want to change one thing as I go through my experiment. I only want to manipulate one variable. So we have the manipulated variable. That's the one that I change. Manipulated variable in my flashlight idea would be the batteries. That's the variable that I change. The responding variable is the one that's dependent. So responding would be, hey, I got light. Okay, that's my variable. The light does work or it doesn't work in my example of my experiment. And we're talking about a scientific experiment. We might be talking about trying some new plant food on a plant. And if we put this great plant food on and all the plants die, we don't know, well, did I forget to water the plants? Is there some other factor? Was all the plants genetically bad when I got them? So I would want to have somewhere I do change one thing, somewhere I don't, and I could compare those two things and see what happens as I go through that. And then from that, if we're talking about scientists, we might create a theory about some of those different things that we've been doing. A theory is simply a well-tested explanation. Now, be aware of this. Theories are not proven. In fact, you can't prove a theory. A good scientific theory you cannot prove. You can only disprove scientific theories. So a theory simply explains why we see things the way they are. Explains what we see as the facts and then puts an explanation to it. However, if somewhere down the road we've got something that disproves that theory, then we have to throw that theory out and create a new one. So there's some common theories that you hear about, like Big Bang Theory. That's how they believe that the universe was created from, at one initial point in this big explosion. That's a theory. We can't prove that. We can't go there. We haven't been there. We can't see it. Now, let's say you came along with some facts that showed that just wasn't possible. You could then disprove that theory, and we would have to come up with a new one. Okay, so we can't prove theories. And then we have scientific laws. And scientific laws are different from theories. Scientific laws are more just statements of what happens, but they don't try to explain it. In other words, think about this. We talk about the law of gravity. Law of gravity simply says we know that if we drop something, it's going to fall to the earth. Basically, the law of gravity simply says that two objects attract each other. That doesn't try to explain why it works. Now, you can go on and explain it. There's actually Einstein's theory of relativity explains gravity nowadays in the way that we believe it works. That's a theory, though. That's not the scientific law. Okay. Einstein's theory says, well, that space is bent around objects that have mass. And just like marble rolling down a hill, it's kind of the same kind of thing in a sense. That's a pretty basic explanation, but that's kind of where it goes to. But scientific law simply says, hey, we have these laws. We know that if we drop something, it's going to fall to the earth. Or Newton's laws of, motion. We talk about his first law of motion, the idea of inertia, or second law of motion, force equals mass times acceleration, and action reaction for third law. Those are examples of scientific laws. They don't explain, they just give relationships between those. That's the difference. All right, if you're a good scientist, you really want to collaborate and communicate. This is where you get to be famous. Okay? To be honest, if you're really a true scientist, you want to get your information out. You want to have people know about it. You want to get credit for it. And the nice thing about scientists collaborating, communicating, is it is much more likely that we're going to learn stuff, that we're going to have a more successful outcome. One of the reasons why science has advanced more quickly in the last 20, 30, 40, 50 years than it did in the thousands of years before that is because of our ability to do these things, collaborate and communicate. The internet, an incredible thing for collaboration. Somebody discovers something, and 5 minutes later the entire world can know about what happened. You couldn't do that, Think about it a couple hundred years ago. If you discovered something in Europe, it might take years before it got to the United States. Well, it wouldn't be the United States, got to the New World. Okay? That's the thing. It took that long for anything to happen. Nowadays, it's instant.